So good morning and welcome to the second part of our Data Science Africa Summer School. This morning we are privileged to have Charles Saidu, who is a lecturer at the African University of Science and Technology in Abuja, and is going to be taking us through an introduction to Gaussian processes. So Charles, please, you can start. Over to you.
Good morning, everyone. My name is Charles Issa Saidu. A slight correction there. I'm a lecturer at Bayes University, but I'm currently rounding up my PhD at African University of Science and Technology. So yeah, that's the short brief. So today I'm going to be walking you guys through Gaussian processes. Just a simple introduction. To get started, I would like us to be on the same page and walk through the Python notebook that I've prepared. So I'm going to be sending the link. I'm going to be adding the link here, I guess. It's in my repo. I don't know, Martin.
Yes.
Is it possible for you to help us to walk us through setting the link up on the?
Okay.
Yeah,
I can. So I'm going to. Can you share the link first in the?
Okay. So yes. Okay. So this is the link. So I'm sending it to the panelists and so that's it there.
Okay. 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 So I'm going to try to share my screen and let me try to share my screen such that we can all. Okay. So I'm sharing my screen. So for those who are able to see my screen, can you write something in the chat? Those who are able to see my screen, write something in the chat.
Okay, cool.
Okay, good. Good. Yeah, so so there is this link I'm going to share in the chat. If you can click that link, that I put in the chat, and then you try to paste this link that Charles has sent. You see how. Oh, okay. So what you're going to paste is this. What you're going to paste in there is this. What you're going to paste there is this. And then when you do paste that, you get when you paste that, you will get this, and then you can choose the presentation.
I think I renamed the folder, so
you renamed the folder
one with underscore, yeah. Yeah, so I think you just passed it.
This one here.
Gaussian processes. Yeah, that should be it.
It's this one, I think. Huh? It's this one.
No. Yeah, that's it.
So I don't know if has anyone been able to access the IPython notebook, this IPython notebook that is showing? Can someone type something if you've been able to access the notebook? Okay, so Jeremy has been able to. Andrew is loading. Okay.
Okay.
Do we have more people who have been able to access it?
Okay.
Okay. Now, good morning, gentle people. Speaking of GitHub, when I open my page on GitHub and the green button that usually has download all clone. Yeah, so what we're trying to do is to make sure that we run the notebook within Colab such that we also benefit from the processing power, online. So there is no need of cloning and downloading it now, but later maybe people can download it if they so wish. But if we could all run it in Colab, that would be great and faster for Charles to start.
Okay. Well, I'm not presenting now, so maybe when I do, I'll try to make the text larger.
Okay.
Yeah.
Okay. So I think, can we start now?
Yes. So, okay, I think we can start. So I'm going to stop sharing my screen, and then Charles, you share yours, and you can continue with the presentation. Okay.
All right. So, I'll be. So I think Martins, I think you disabled host sharing. Yes, for me.
Okay. It's okay. Let me try to. Yeah.
And also the video. So. Just
No. So I've just cleared that. You can go ahead now.
All right. So we start here. We start to. Let me see. Okay, so good morning, everyone. Well, it's morning here. We're still very early. I don't know if you can, if the screen is bold, if the font is large enough, can you just indicate by typing something on the chat? If the font is large enough, I mean, legible enough for you to see. Okay. All right, so like I said, good morning. My name is Charles, and the purpose of today's talk is just to give a slight introduction to Gaussian processes. So I'm going to try to do that from the angle of the normal distribution and the multivariate Gaussian distribution. So before I continue, this slide was largely motivated by Professor Lehel, Professor Neil. A good number of the slide items in the slides were obtained from Andreas. I'm sure you guys have met him in the deep learning class. Okay, so with that said, we'll start. All right, so the first thing I want to do is to basically walk through a probability density function. So now, a density function, especially for, hello? Okay. So the density function for a continuous random variable is a function of a random variable whose integral across the interval gives the probability that the value of the variable lies within. So what we're saying in essence is, for a continuous random variable, there's something called a density function. And that is this f of x. So the density function is a positive, must be at least 0 to some positive number. It's a number such that when you integrate it, you get a probability. On its own, it is not a probability in itself. It's not a probability for the random variable. However, if you integrate the density over a particular integer interval, what you get is then the probability. So random variable, okay, take the value between A and B. Okay. Now, also another property of this continuous density function is that for it to be valid, the integral over the entire space must equal to 1, and that is from basic probability that we know. If you integrate, if you replace A, B here with A, and you do this integral, what you get is 0. Okay? Recall that this is a continuous density function. So what that means is you cannot, the probability of a particular point, okay, in this space, in this case, is 0. So which really makes sense, because I mean, we're dealing with continuous random variables. So we are looking at the probability is defined over a particular area which you integrate. So having said that, so I define what a Gaussian distribution is, and I believe everybody has seen these this density before. And let me also recap that I write it as f of x because I don't see these as a probability. Like I said, it's the function, it's a positive function, 0 to some positive number that when you integrate, you get a probability, a probability. So for a Gaussian distribution, the density is given by this fairly ugly equation, 1 all over the square root of 2 pi times the variance times e to the power of -½ mu minus x all over sigma square. It's fairly straightforward. So it just tells you that it just gives you the density of some distribution. And if you plot this, what you get is a bell curve. Okay? It is symmetric around the mean. So which means that for this Gaussian, univariate Gaussian, the mean and the median are the same. So what I did here was to sort of demonstrate, to see how this density function behaves. And here, I basically import the matplotlib, the numpy, the scipy, which is a statistical package. And then these ones are for interactive and Jupyter notebooks. So we can change the parameters within the univariate Gaussian and see what we get at the end. So that's what this first cell does. The second cell here just basically codes this function, okay? It is univariate because the input x is just one dimensional. So if I get an input x, a mean, and a sigma, I can return this entire function, okay? So this univariate PDF is what I have here. So I define this function, and then I can plot it. So to plot it, what I need is the mean and sigma, okay? And I'm assuming the x value range between -10 to 10, and I have 100 points. So the plot function basically plots the x versus the PDF of the x, okay? And then the next cell here is an interactive cell that basically allows me to modify the mean and the sigma the mean and the sigma, such that once I do that, it replots based on the new parameters that I've entered. So this is what it looks like. Okay, so why do I do this? Like I said, the Gaussian density is symmetric around the mean. Okay, so if I want to see the behavior of this density function, okay, that I've coded here with the interactive plot here, I can basically just look at how it behaves. So this is the mean 1. So if you look at this point, you see that most of the data is concentrated around this point. The sigma in this case is the spread of the data. So if it's say 2, it means my Gaussian density is a lot more spread out. 3, 9, and in that order. Okay. So it's fairly simple. It's what we already know. Okay. But I need it to explain what I'm about to talk about in the next slide. So one interesting property about this Gaussian density is that if I scale it by mu and sigma square, what I get is also a Gaussian. And you can do that fairly by just bringing out a piece of paper. Okay, if x has a standard Gaussian, that is the mean is 0 and the variance is 1, okay, that is something like this. Okay, the standard Gaussian. I can scale this random variable by multiplying it with another positive number x and shifting it by the mean. What I get is also a Gaussian random variable. Now this is very important because it means then that if I want to sample, that is draw random samples from a Gaussian with any mean and any variance, all I need to do is to draw a standard Gaussian centered at 0 and variance 1 and scale it. And what I get is the equivalent of what I need. So I show this in pictures by drawing 1,000 random variables, random samples, okay, that are all standard normal. And then I plotted it, okay? All right, so this is what I get. Just same thing as this, but this time I'm drawing random samples and there are 1,000 of them. So if you look at this the graph you get here, you notice that most of the values are concentrated around 0. So this is a standard Gaussian, which means 0 and unit variance. So now what I did here was to scale this value. So when I scale it, okay, what I want is actually a Gaussian that is centered at mu and sigma square. And what we're saying in essence is, if I multiply the mu with that random variable and add if I multiply the variance with that random variable and add the mean, what I also get is a Gaussian distribution. Okay, so here I define that scaling that we are talking about. So I define a scale Gaussian as a function with mean, mu, and sigma that, okay? And that is equal to z, which is exactly what we have here, okay? So z, for example, in this case, becomes the sigma times x plus the mu. And then I also plotted it, okay? So to show the interactive plot, so what I want to do is to vary mu and sigma, okay? And see whether I get a Gaussian, a Gaussian just like this, but with a different mean and a different variance, okay? So that's what I have here, all right? So this means that, so this blue Gaussian is the original one, which is this, okay? This is the scaled version. So obviously, if I'm scaling with sigma 1, I expect to get the same Gaussian as this, okay? The same thing, but shifted by mean 2. If the mean is not shifted at all and is 0, so this, it means my z becomes my x, and what I get is exactly the same Gaussian, this Gaussian density, just as this. Okay, so with this interactive plot, it shows me that I may decide to get one density shifted by some mean. Okay, so now my new Gaussian density is centered at 4. Okay, but it has sigma 1, so it's exactly the same spread between these two. Okay, I may decide that I want to scale it by 3, so I get a different spread, okay? But it is still roughly around 4, I mean 4, but it's a lot wider, okay? So this is a density derived from this density. Like I said, it's very important because when I'm now writing these programs, okay, if I know how to sample a standard normal distribution, then it's easy to start to sample a Gaussian of any mean and any covariance, any variance. So that brings us to the next part, which for some might be easy to understand, but for some maybe not so. But what this basically means is that in the case of the univariate Gaussian, the random variable is a real number. It is not a vector, okay? But for a multivariate Gaussian, what that means is the random variable x is a vector. It contains several variables. And in real life, in data modeling, this is what you mostly find. You collect data, okay, and collect features. So those features, you can regard them as the variables within the random variable x, okay? So you can look at this as one sample, okay? All right, that is characterized by several variables within. So you have a vector, okay? So the question is, we can now extend this notion of Gaussian to a vector in d dimension, okay? Now, just like the univariate case, we can assign a density to this vector. Like I said, remember, this is not a probability. The density is a function that can either be 0, okay, or some number greater than 0. It just describes how, let me use how dense, okay, that random variable should be around the mean and around some, in this case, covariance. So this is the density for my random variable x. In this case, x is a vector, and it's a d-dimensional vector. Just like the mean, just like the univariate case, excuse me. Just like the Gaussian is characterized by the mean vector and the covariance, okay? So this is the mean here, and this is the covariance sigma, okay? In the univariate case, we saw that the mean basically describes the concentration of data around its points. The same thing with the multivariate Gaussian. The mean describes how concentrated the random variable is to that point, which is the mean. The covariance, which in this case is sigma, describes how the variables within this random variable, within the x, are related. Okay, so we expect the sigma to be a symmetric, especially for a Gaussian, to be symmetric and positive definite. So what that means is this whole thing here, okay, should give you a positive number or 0. Okay, this is a matrix. Okay, the sigma here, the covariance here is the matrix, such that if you take the transpose of that matrix, you get the same matrix. Okay, and that's what the symmetric property means. Okay, the positive definite means that if you take any vector and you get the quadratic form of if you get a quadratic form of this covariant matrix, what you get is either 0 or a number greater than 0. Okay, so this is very important because once this matrix is positive definite, it means we can easily find the determinant of that matrix, and this entire function will not blow up in our face. Okay, because if the determinant here, because this is the determinant, if it is 0, then it means we are dividing something by 0, and this will blow up in our face. This is infinity. Okay, all right, so our multivariate Gaussian in this case is similar to what we have here. Okay, only that my x is d-dimensional in this case. Okay, now this is very important because this has a strong relationship with Gaussian processes, and you'll see in a moment. The covariance matrix, okay, is defined by this nasty looking thing here. We're going to come to that in a moment. So what I try to do here, okay, is to visualize what a 2D Gaussian looks like. I can't do for 3D or 4D or whatever because there's no way to visualize that. Okay, so for 2D Gaussians, what that means is my random variable x has only 2 variables. Okay, and we want to look at the density of that in a 3D graph of that density. So for d is equal to 2, so what I did here was to import some of the tools that I will be needing to do this visualization. So the first one here is some Axis 3D from Matplotlib toolkits. And then here, I import the color map, okay? So for this very demonstration, I want my graph to appear outside my Jupyter notebook. So basically what I did was to specify that the plot should be QT. I really don't know what QT stands for, but this is basically how it's done. Okay, so run this. All right, so here I define this function here, which is the multivariate Gaussian density. And basically what I just did was just to code this entire thing here. Okay, first of all, I get the determinants of the covariance, which is sigma. Okay, this constant term, this whole thing here, okay, is what I define here. 1 all over the square root of 2 pi times this determinant. Okay, this x minus mu is the vector I get when I subtract x, the random variable, from the mean. Okay, all right, and then the fractional part is what I define here. So what I get here, which is x underscore m transpose, is this one here. Okay, and I do the dot product of that, okay, with this term here. Okay, I could easily have coded this as the inverse of the covariance, okay, dotted with this x. Okay, but a simple way to do that is just to do lean solve. I don't know if we can, let me bring up, let me do something here, just a moment. Okay. All right, so, okay. So I don't know if you guys can see a writing pad. If you can't, can you just, okay. If you can you just type something on the screen? If you can see the writing pad, can you just type something on the screen so we can continue? Okay, cool. All right, so what I'm saying here is this, okay? What I did here was to try to code this entire line, okay? Which is x minus the mean transpose the covariance inverse x minus mean, okay? So this quantity here, okay, is a matrix multiplied by a vector. This is going to give you a vector, okay? This is also a vector, all right? So by the time you do the dot product between the vector, between two vector, you get a number. So the entire thing here is going to give me a number. And because this is positive definite, what you get here, the entirety of what you get here is either 0, okay, or a positive number. So you take the exponent of some value that is either 0, negative 0, or the positive of that number. Yeah. So, but what I'm saying in essence here is, if you notice, I coded this part as lim solve of the covariance and x minus mu. Okay. So this is basically from linear algebra. So if I have x, okay, this covariance times, let's say a, okay, and that is equal times b, and that is equal to x minus mu. I can rewrite this whole thing as ax is equal to b, okay? And this is a matrix, this is a vector. I can pre-multiply this by its inverse. So I have inverse of a, x, and this is inverse of a and b. So what I get here, x, is a inverse of b, okay? In Matplotlib, I can simply solve this equation, okay, here by doing this, okay? Lean solve, I'm saying this because we're going to need it in a moment as we continue. Lean solve of covariance matrix and that vector, okay? So So what I did here was say lin solve, okay, of cov and this vector. This is equivalent to writing the covariance inverse dotted with x minus mu, okay? All right, and that's what is here, okay? And then I do the dot product of the transpose of this with whatever I get after doing the lin solve of that. So at the end, okay, I take the exponent of that, okay, that is all this here, multiply it by the constants which I've defined, and I get this, okay? All right, so the next thing is, what I try to do is a 3D visualization, because this is 1D, okay? So what I try to do is a 3D visualization of this multivariate, okay? In this case, the dimension is 2, all right? So what I did was to do a mesh grid. So let me do this. So what I did was to do a mesh grid. There's this line, this first line here, okay? What I intend to have is a 3D visualization, okay? Where this z-axis is the density, is the PDF, okay? And then I have one axis and I have another axis, okay? This is the first variable, x1. This is the second variable, x2. So this mesh here, okay, is what I call, okay, x1 and x2, all right? So with this mesh here, I can then loop through, okay, and calculate the multivariate normal based on the density, okay? That is the z part here, okay, is a function of x1 and x2. And that's what I have here, okay? So the next thing is just to plot it, okay? All right, I do a 3D projection, and I do a surface plot and label the axis, okay? And then you can visualize this. For some reason, I have to run it several times before it appears outside my Jupyter notebook. So let me try it again and try this again. Okay, I need it outside my notebook so that I can turn it around, I can spin it. So this is what I get. Okay, so as you can see, this is same thing as what you have in the univariate case, but our x now is random variable containing 2 variables within it. And on the z-axis is the density. I can spin this around, okay? And as you do that, if you spin it to the point where you have something like this, okay? The red spot indicates the places where you have the variables concentrated, okay? And if you look at this, really, you have sort of some cycle, okay? And this tells you that the variables x1 and x2 are not correlated, because if they are correlated, what you get here is not a cycle, you get an ellipse, okay? And if you spin it around, you will see that this is saying the x1 variable, the mean of the x1 variable is centered around 0. You can see the peak here, okay? The mean of the x2 variables, okay, is centered around also 0. So this is a Gaussian centered around mean vector 0, 0, okay? And a covariance matrix 1, okay? So it means it's basically an identity matrix, okay? Now, having said that, the beauty with these multivariate Gaussian is that they come with some very nice property. Now, these properties is what I illustrated here. It can be really intimidating, but let's just see how we can break it down. So if I have a random variable x and it is d-dimensional, okay, I can decide to partition that variable. So this is supposed to be from x1, not the whole function here. So that's a typo. Okay, I can decide to partition that variable. That is, I will have a collection from 1 to some point s, and I call that xa, and I have from x1 to d in this case, not n. Okay, to d. This is also another typo. Okay, so here we partition these random variables into two vectors. Okay, and we want to investigate the properties of the joint between, in this case, the joint density between xa and xb. And we say that that is also Gaussian. Okay, so if we partition this, okay, the joint of that is Gaussian. And this is true because the entire thing we assume that is Gaussian with mean with mu and k. This is supposed to be sigma. Okay, so the joint density is also Gaussian, and its covariance is given by this. So if you look closely, you see that xa, okay, xa has a mean of mu underscore a. It has a covariance matrix of xaa, sigma aa. Xb has is xa. Just seen a lot of typos. Nice. Okay, I'll correct this in the repo. XA, so this should be XB. Okay, XB also has the mean mu B and a covariance BB. Goodness, this is supposed to be BB. Okay, a covariance BB. Now, this covariance describes how XA varies with XB. That's why it's called sigma underscore AB. If this is a symmetric matrix, if you take the transpose of it, you should get the same thing. Okay, but for convenience, what I did was to say that this part here indicates the covariance between XA and XB and XA. Okay, but if this matrix is symmetric, it means this quantity here will be the same thing as this quantity here. Okay, so this is known as the joint. Okay, the marginal density, okay, can be given by these joints, but you integrate out the second variable. So the marginal density of XA, okay, is the same thing as the integral over the space of XB of the joint, okay? And what you get is also a Gaussian with mean XA, which is, if you read it off, it's the same thing as this point here and this point here, okay? But what is really striking, which is what we're going to be using a lot for predictions in the Gaussian process, is this very property, which is really sweet. It says that the conditional is also Gaussian. And we can write that conditional as the density of XA given B, okay? That is also Gaussian with the mean mu bar and sigma mu bar. What are these quantities? These quantities are this, okay? So obviously, you see that the mean here, okay? The conditional mean here is the mean of A, okay, plus the covariance between A and B, okay? And remember that lean sum I told you about here, okay? This is the vector, okay? Or it could be this is the vector. This is also a vector, and this is the matrix. So this is going to give you some number that is either positive or 0, okay? So if we assume that ab initio that our joint has a mean of 0, 0, then this goes off, this goes up. So the term you're going to see is only this part. The covariance, on the other hand, for the conditional is just an adjustment of what we already know. That is the inverse of BB, okay? Multiply dotted with sigma BA, and also dotted with this, okay? You don't really have to cram all this, okay? What I'm just going to do is just to try to quote just this conditional, to try to explain the concept that we're talking about. So just as before, I try to visualize all this, okay? To see how it really looks like, okay? But in this case, I do it for a bivariate Gaussian, just the same thing as this, okay? So what I try to do here is to say, well, okay, I assume I have a Gaussian, a multivariate Gaussian, the dimension is 2, okay? And I define this sigma S11, okay, to be this, S12 to be this, S21 to be this quantity here, and S22 to be this quantity here. What I'm trying to do is to investigate this conditional density. So I say if I know X2, just like this, okay? Hold on, please. Give me a moment, please. Okay. All right. So what I try to do is to see what happens with this conditional, or in this case, for a bivariate Gaussian. So if I know, I assume for a start that I know that X2 is -4, okay? And I know that the mean between X1 and X2 are about 0, 0. How would the Gaussian look like? Okay, and that is what this is all about. Okay, this is the mu, this is the sigma as collected from these parameters. Okay, I do this, okay, as lane sum of all this, okay, and the estimated mean, which is this guy here, is that you can read off the code and it's fairly easy. The remaining part is just a plot. Okay, it's a 3D plot of the Gaussian, what it would look like. So when you run this, and I do an interactive demonstration of that, okay, what you get is this. Okay, so this is the density. You can spin it around. Okay, what I'm saying, what this means is, if I know that X, this is my X2, if I know that X2 is 4, okay, what would the density look like? That density is still a Gaussian, okay, and this is this line here, okay. It is symmetric, and the mean is the same thing as the median, so we have this shape here, and I just replotted it here, okay. I can interact with this. Suppose if I know that X2 is 9, okay, so we displace, so X2 in this case is 9. So this X2, its value is 9, but it means that what will be the density, which is now going to be only a function of X1, okay? Think of this as putting a slice, putting a knife, okay, around the part where X2 is equal to 9. So what you get is still a Gaussian, okay? So you can play around with all this, okay? This is just a visualization of that. Okay, now you recall that at the beginning, I said, if I know that a univariate Gaussian, if I have a univariate Gaussian, I can scale it, okay, to a mean of a mean and a variance, and I demonstrated with this. You can do the exact same thing for a multivariate Gaussian. Okay, so this one says if I have a standard normal, if X is a standard normal, then I can scale it, okay, so that I get a new random variable Z that is, okay, X multiplied by some matrix plus the new mu, which are all in D dimension, okay? And this is very important because that means that I can draw samples from these multivariate Gaussian given any mean and any covariance, okay? So I'll go back to the screen again and show you guys what I'm trying to do, okay? So what I'm saying here is, if my random variable X is D-dimensional, okay? All right, so with any mean and any covariance, if I do a random draw of this variable, so for example, if I do maybe X1, this is going to contain variables X1, X2, blah, 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 XD, okay? If I do another random draw from, okay, from this in the X2, I'm going to get another vector, which is D-dimensional, okay? So the idea is, once I do this draw, I will just plot the values as they are, okay? And that's what I do, okay? So I do a random draw and I just plot the value. If you notice, since this is a multivariate Gaussian, for D that approach infinity, this our random vector is going to be infinite dimensional, okay? So it means I can draw an infinite dimensional Gaussian from the multivariate Gaussian and then just plot the variables. And that's what I did here, okay? I specify the mean, which is D-dimensional. I specify the covariance. In this case, the covariance is an identity matrix, okay? And I do a random draw, all right? All right, and what do? I do a random draw of a particular value, in this case, 2, and then I just plotted it, okay? So what I get here, okay, is this weekly thing. So a single line is a random draw from a multivariate Gaussian, okay? In this case, I have 2, okay? So let me change the dimension to maybe 1. It's just a point, you won't see anything. Okay, if there are 2 variables in the random in the multivariate Gaussian, it's just 2 points. This is the first point, and this is the second point. Okay, for the first vector, this is the first point, and this is the second point for the second vector. Okay, if I want just one draw, this is just a line. Okay, so if I increase D, I get this is 3 points. This is 5 points. 1, 2, 3, 4, 5. 10 points, okay? So I can take D to infinity. What I get is an infinite dimensional vector. I can treat that as a function, okay? This is 1,000 points, okay? The N here indicates the number of times I draw from the multivariate Gaussian. So let's say this is, let's say this is 10. Let's say I have just 80 dimensional, and then I draw that, okay? So it means here, what this means is I have drawn 30 random vectors, okay? Each of dimension 80, okay? And I just plotted it along the axis, okay? Remember, within this code, I said these random vectors, they vary depending on this covariance matrix. And the covariance matrix in this case is an identity, okay? And what I did was just to plot the heat map of that, Okay. So as you vary the number of variables within the random vector, this changes, and then you have the covariance. So the covariance here just says, well, if you read this line, it means along this axis, this is 1, 1, 1, 1, 1, and 0 everywhere. Okay. If there are any questions at this point, maybe you can let me know. If there are none, we can continue. Any questions so far? Just type something on the chat if you have a question. Or if you have any questions as we continue, you can always send a chat. Okay. So having said this, my claim is if you know this, then you are about 80 to 90% okay with Gaussian processes, because Gaussian processes are just basically multivariate Gaussians. Okay. Displayed in this form. Okay. Now, these wiggly functions or wiggly vectors, okay, are determined, the shape of this is determined by this covariance D. Okay, and we see that in here. So here, what I just did was, instead of making the covariance an identity matrix, okay, I made it some collinear matrix. Okay, I pick a random sample of D dimension and I made a collinear covariance out of it. And I did the exact same thing. Okay, what you get is a function looking differently. Okay, while this one is all wiggly, you can see this looks totally different. Okay, let me just draw one random vector. So you just have a line. Okay, let's draw maybe 26. So there are 26 lines. What you have here is totally different from what kind of function you have here. So this basically says that these random vectors, the way they appear is strongly determined by the covariance matrix. Okay? And then if we change the covariance matrix, obviously we change the shape of these random vectors. And of course, the heat map for this covariance matrix is plotted side by side as that. So having said that, I think it's now is the time to introduce what a Gaussian process is. So a Gaussian process derives its idea from these multivariate Gaussians. Okay? Now, a Gaussian process is a collection of random variables, any finite number of which have a joint Gaussian distribution. So equivalently, a GP can be seen as a stochastic process, which corresponds to an infinite dimensional Gaussian distribution. The same thing as what we have basically just talked about here. Okay? But what is this? What is the slight difference? So what constitutes the random variable in this case? We call it F. Okay? So what we are saying in essence is, for a Gaussian process, in the case of the multivariate Gaussian, if you recall, we said X is D-dimensional. Okay? This is the multivariate part. Okay? Now for the Gaussian process, it's identical to this. In place of this X, I'm going to have F. Okay? And I'm going to see F. So let's switch that a little. It's n-dimensional. And n is the number of samples. Okay? So I can form F, which is a vector, as fx of 1, comma, fx of 2, comma, blah, 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 xf of n. Okay? So this is the function evaluated at x1, the function evaluated at x2, the function evaluated at xn. Now, the x, oh goodness. 1 minute. We just had a power outage. Just give me a few minutes to switch over.
Yeah, so I guess the good morning, participants and all. So as Charles prepares, we are slowly gravitating behind time. But if you have any questions, please post them in the Q&A. There's a Q&A just down on your screen, so you can post them there, so we can have a quick Q&A once Charles wraps up.
Okay, so sorry about that. Oh, I think we are running behind schedule, and I'm not even halfway. Okay, so let me see if I can quickly round off. Okay, so all right, so the point is, if I collect all this, okay, then I have a d-dimensional f, okay, and I can fit a Gaussian to this with some mu and some sigma. But the bottom line is, the main fact is, how then should I design this Z? So it turns out that, I mean, if you do after some complex mathematics, it turns out that you can relate the covariance matrix with this X, okay? So I can define K and K star with some function, so, okay? The dot product of something. And then what I get here, okay, is a positive definite function, which I can use to characterize this multivariate Gaussian, okay? And just like in the case of the multivariate random variable that we saw, that function is that matrix is going to determine the behavior of the collection of these functions. So the entire thing here is a vector, okay? We can fit a Gaussian to it, all right? And then the beauty is, if I now have more examples, x1 down to infinity, what I get is also an infinite dimensional f, okay? And just like I did with the case of the univariate Gaussian, the multivariate Gaussian, I can sample that, okay? Since we are out of time, the function f, that vector, okay, has a covariance called k, okay, which is the function of the input at x. And like I said, just like you saw within when I demonstrated this sample draw and with this sample draw, if you change the covariance k, which is a function, you get a totally different function which you sample, Okay, so in general, what you have when you do Gaussian modeling is that you collect data, okay, X, all right, and their function evaluationals, and maybe some Y, all right? So these are your data, you collect maybe 5, blah, 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 okay? And their corresponding values. So this may be 1, 2, 10, 8, blah, 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 which basically you sort some index set. And you get their corresponding value, 2, 10, 11, maybe 0, blah, blah, blah. You can then pick the entire thing here, okay? Fit a Gaussian to it, all right? For the covariance, you pick the entire thing here and form a covariance matrix from it, okay? Once you do that, what you get is the Gaussian process, okay? And this is what I showed here in the noiseless case, okay? And because F is a multi-dimensional Gaussian variable, all the properties that we talked about here, everything here as they are applies. And we can simply just code them. And we can simply just code them, okay? The joint is valid, the marginal is valid, okay? And the condition is also valid. If you look closely, you will notice that this is exactly the same thing as what you have in the multivariate Gaussian case. And we can just basically code it. For the noise model, which is a general thing, is as you are collecting the data, you assume that it is corrupted with some noise. Okay? Which is ideal, especially when you deploy sensors to the environment, and then sometimes the reading may not be exact. So you assume some noise. If you do that, okay, then we can model the entire thing also as a Gaussian process. Obviously, Y here is going to be f of x, this one, okay, plus the noise, these two. And that's what gives you Y. So I can pick the entire thing here, okay, and treat it as a multivariate Gaussian, okay, with some covariance, everything here, okay. But this covariance, because my X is corrected by noise, this covariance will incorporate the noise factor. And that is, okay, and that is what I have here, okay. If you do both of that, what you get is a Gaussian process. So the punchline basically is, okay, you have all your data points, okay? You have all the function evaluationals, and then you pick the entire thing and fit a multivariate Gaussian to that. If you do that, what you get is a Gaussian process. And that is what I coded, okay, here. So at first, I define that covariance function, which you see once you read up the note, okay? I'm demonstrating with two types, the collinear one, which is the one you saw when I was doing the multivariate Gaussian, and something called the RBF kernel, okay, which is defined here. All right, and then, okay, sorry, I think okay, so run this and run this. Okay, so these are what you get here are the various kernels with their parameters. So each of these Ks have some parameters like the sigma, okay, the length scale, and well, basically. So what I did here was to show how these kernels look like, the samples you get when you use them, okay, and their covariance. So this is for the RBF kernel. So these are the kind of samples you get for length scale equals 0.5. As you increase the length scale, okay, you get a more, well, how do I describe this now? The the shape of this thing changes. And I think basically you can actually see it as you from this visualization. There are many of these kernels. Okay, you can, in fact, you can actually combine them to get a different Gaussian process, and that's what I showed here. Okay, for different kernels and different parameters and the combination of some of these kernels, and that's what you get here. So this is the RBF kernel. Okay, and this is the sample you get from it. Okay, this is the covariance. Okay, this is a kernel called the Martin. Okay, this is the kind of samples it looks like that you get. This is the periodic, and this is the kind of samples, and you can also combine, like I said, this is the constant kernel. So here, what I show is a demonstration of how these things really work. Okay, so as an example, I assume I have function evaluation and these are corrupted by some noise. Okay, so basically what I have is f of x, y is equal to some function evaluated at some point plus some random noise. And I assume that, so this is without e. So, and I assume that f, the true function, is given by this. Okay? So what I'm saying in essence is I want to see how we can use Gaussian process to model this kind of event. Okay? So do some importation. I define this true function, which I'm going to learn. Okay? All right? And assign it to f underscore x. The sigma is this guy here. Okay? So I say my y is f of x plus the noise, which is the entire thing here. Okay? So this is what it looks like. Okay? The red line is a true function. Okay? The dots are the data collected. So ideally, in real life, you probably will not see those red lines. You see something like this. Okay? And we're trying to learn the underlying function or something that tries to predict this kind of behavior. Okay? So to get better understanding of what we're doing, so I included this just to show you that this is what we're interested in doing. Okay? So just like before, I get some test data. Okay? That is before I've seen the data. Okay? This is what I want to test my model on. Some of you doing machine learning, you probably understand what I mean by that. So before I see the data, okay, I want to assume that I have some prior knowledge of how the function will behave. Okay? And that is defined by the covariance matrix. In this case, I use the RBF kernel. Okay? I do that, and I draw random samples, multivariate Gaussian samples, based on the RBF kernel, and I draw a few of them. Okay? So before I see the data at all, this is what I have. Okay? All right? Now, I'm almost done. So think of my test point as a partition. So my test point x test is a partition. Okay. Now that I've seen the data, okay, I can simply observe a joint or a marginal of the test point and the data. So my data maybe is x1, x2, blah, 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 up to xx, then plus x test. Okay, so I can now observe a joint between these two. So, but I know this guy, okay? All right, so what I'm saying in essence is I can look for the density of this what I know, which is x train, okay? Sorry, the density of x tests given the x train that I know. Because the whole thing is a multivariate Gaussian. Okay? And then I can also find the marginal of that based on this ugly looking formula that you see here. Okay? Based on this ugly looking formula. This is the marginal. Okay? This is my test. Okay? This is my training data, and their corresponding y values, okay? And this is my x test. And we say that that also is also Gaussian, given by this mean, okay? And given by this covariance, which is exactly the same thing as you saw with these properties, okay? But for a Gaussian process, I'm assuming that the mean is 0 and the mean of those points is 0. So if this is 0, if this is 0, all you have is just this as the mean prediction. And it's the same thing as here, okay? All right, but the covariance in this case is determined by this k. So this is the covariance of the test point and the training points. This is the covariance of the entire training point, and these are the y values. You can code this, simple. Okay. So what you do, okay, what you get is the posterior function after seeing the data. This is before you see the data. It's all wiggly and all that. But by the time you condition on what you know, okay, and you get the posterior function, you have this wiggly function, which practically describes how the general underlying function behaves. Okay, but remember that when we're talking about these kernels, we said they come with some parameters, so you can actually fine-tune those parameters to get better performance. Okay, as it is right now, the error is much larger because it doesn't really fit very well. Okay, to get a perfect fit, we would have to tweak the parameters of the kernel, and that's what I did here as an interactive plot. Okay, so if I adjust the variance or the length scale to some value, what I get is a better fit of the function. Okay, so the question is, in practice, how would you modify these parameters? Okay, and yeah, also what I did was the test point is within the training point. Okay, not exactly, but within it. So that's interpolation point, and Gaussian processes perform very, very well within interpolation point. If you have a test point that is slightly outside the training data, okay, this is what I showed here. All right, so at this point, this is the prediction after the training data, and you don't want the model to be overconfident. Okay, you want the model to say, well, I really at this point I really don't know, especially as the data points are very, very far away from the training point. And this is what this shows. So let me just tweak this a little. You see that at the point away from the training data, the gray part is the variance. It's the same, and it's just saying, well, I don't have much confidence in the prediction that I have here. Okay, so I'm just going to revert back to my initial assumption of mean 0. So if you trace this line here, you see that this is actually mean 0 for this function. Okay, and this is the equivalent the heat map of the covariance of the posterior. Okay, so I mean, you guys can read up this. These are some of the advantages of using these Gaussian processes. Because first of all, they are full probabilistic model. Okay, they are not overconfident. For points far away from the training sample, they basically go back to say, well, I really don't know. Okay, and you want models like that. You want some form of uncertainty estimation when you make predictions. And Gaussian processes are very, very good for that. You can also use these Gaussian processes for Bayesian optimization. I think Andreas is supposed to talk about that. Some online learning setting and active learning, which is what I do a lot. Okay, so finally, how do you adjust these parameters? It's actually called model selection. So it turns out that you can actually optimize this function. I didn't do that in this slide, but I left it as an exercise. It turns out that you can actually optimize the marginal likelihood, which is sometimes called the evidence. Okay, you can actually optimize this based on that parameter because it's Gaussian. So what that means is if you differentiate this, set it to 0, okay, you can actually get the function point at which the predictions are maximized. Okay, and there are many ways to do that. Okay, but what I just try to show here is a contour plot of the possible values that you might want to tweak your predictions to. Okay, so I did a contour of the log evidence, okay, which is this, all right, over the length scale and the variance, okay. So what you get is something that looks like this. So this is the variance, this is the length scale, this is a grid. So this part here is a region where you get infinity. I mean, there's no solution here, okay. Within this part here, it says that if you to get the optimal prediction, you should set your variance to be something around 0 point something, and the length scale should be something around 0 point something, okay? And you can basically go back and check it. If the variance is maybe 0.2, blah, 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 you get better prediction, okay? So in essence, you can actually get this, okay? This log, this evidence, okay? And optimize it to get the optimal parameters for that kernel. And it's easy to do. You can implement this if you're interested, okay? All right, you can pick up a simple optimization packet from SciPy and use it to optimize this function if you don't want to do it analytically, because it also can be done analytically. Just differentiate that evidence, set it to 0, and then you get the maximum values at those points, okay? So what I showed you was just hand coding these processes. You can use there are many libraries. The popular ones, the ones by Professor Neil and his team at University of Sheffield. There's also one in scikit-learn library, and here is is a demonstration of how to use some of those libraries. Okay, so you can go through all this at your own. If you notice at this point, there's an optimization. So let me just basically run this. So this is a data set that I got from Matthew. Okay, I think we presented this in Addis Ababa. Okay, and this is the data set just for a visualization. This point is what we're using as test points. Okay, this point's probably for training and some prediction. Okay, if you're using a GP library, all you need to do is make an instance of a kernel. It has been implemented in the GP. Okay, in this case, I'm using the variance of 1, length scale of 10. And then you also make an instance of the model. In this case, this is GP regression with X train and Y train and the kernel. Okay, you can do a display to see what you have at the beginning, the prior information. Here, I'm using a variance of 1, a length scale of 10, with a noise of 1.0. Okay, I can then do an optimization, which is what I said here. Okay, that you can actually write the code to do that optimization for the parameters within the kernel. Okay, all right. So after optimizing this number of restarts, in this case is 10, and you do a display of those parameters, you will notice that you get a different result. Initially, I started with 1, 10, 0. After optimization, it picks the optimal parameters for our model, for our RBF kernel, and I get the display. And then I can do prediction, okay? View the posterior functions, okay? And this is by optimization. You say the variance is 41, the length scale is blah, 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 and like that. So this is the prediction. So this whole thing I talked about are all encapsulated in this library called the GP library. Okay. From scikit-learn. So in this case, this compares different kernels and how they will react, okay? How they will behave, the kind of functions you get given a particular model you're interested in. Okay, so as you can see, this is the prior with the RBF kernel. This is its posterior. But if you're using the rational quadratic, which is a different kernel, this is the posterior you get. If you're using the exponential sine squared, okay, this is the prior you get, and this is the posterior you get. If you're using dot product as a kernel, this is the, okay. This is the prior you get, and this is the posterior you get, and in that order. So I think that's the end of my talk. If you want to know more, you can read this book, fantastic, okay? You can also get some lecture notes from my PhD supervisor, Professor Lehel. You can also obviously go to Inverse Probability, Professor Neil's website. There are tons of materials there. A good part of this slide was obtained from Damiano's introduction to Gaussian processes tutorial. It's on GitHub also. If you want to look at some mathematics involved in some of these things, you can look at Kevin Murphy's book, The Probabilistic Perspective. I want to thank Andreas, and I also want to thank Matthew Mayhew, as Michael Mayhew actually, that's a typo, for some of his contributions in this material. So yeah, so thank you very much, and questions, if there are any questions.
Great, so we'll give Charles a virtual clap. Everyone, you can clap where you are. Okay, Charles, so there are two questions actually that people have asked in Q&A. Maybe you can start with those.
Okay. All right, so, okay. I'm trying to get the questions. Okay. I don't know. For some reason, I can't see any of the questions.
No worries. I can read them for you. That's
okay.
One question is from Andrew. He's asking, I need to use a Gaussian function to discriminate children ages. For example, 3 years versus 8 years, using heights.
Okay, so that's a classification problem.
Okay.
So what I talked about is Gaussian process for regression. You can also do Gaussian processes for classification. Okay. Unfortunately, it's not in this slide, and time won't really permit. But I mean, if you look at the documentation for GPPy, for example, or even scikit-learn, it talks about Gaussian processes for classification. So what that means is basically you just you practically do instead of getting a real valued output for prediction, you get a class value between some point and some point. So I think you can look that up. It's fairly the same thing as this, okay? Only that the output function is different. So yeah, you can do that. I think you can just go to the GPPy website. There's Gaussian process for classification. It's there. It's very simple. Just a few lines of code. Yeah. Any other question?
Great. So there's a question from Remy. And he's asking, if there's time, can you go over the relationship between variance and length scale?
Okay. Yeah, so the length scale, so I think we can just do an interactive, that's the cool thing about this interactive plot. I think this should give you an idea what the difference is. If I increase the length scale, it means the function stretches, okay? So let's put it at, let's say, 2.2. Oh, goodness. Let me go back here. Okay, so let me increase the length scale, say 0.7. You can see the function which stretches. So the length scale determines how stretched these functions are. The higher the value, the the stretchier it becomes. Okay? I don't know if I answered that question. And the variance, okay, let's see. Okay, I don't know how to describe this now, but the variance is how the function out the kernel behaves, I think, within. Okay, so let's pick let's go back here. Okay, let me pick 0.1 so it matches here, and let me pick a high variance. Okay, so think of it as a colloquial way to put it is the horizontal gap between each function. I think you see it better when I do for extrapolation point. So, okay, so it's here. So look at this part, all right? So if I increase the variance, so let's say it's 1.6, okay? Let me fit it properly. These are the small parameters. So you can get, it varies, the point outside this the extrapolation very small, okay? You can see it has a high variance at this point. And then, okay, does that, I don't know if that, I think that should basically explain the difference. But mind you, these two parameters are only for the RBF kernels. So each of these kernels have their own parameters, which you need to tune. Okay, so in general, what you do is just an optimization of those parameters, okay, given the data points. So any other question?
No other question. I think so. I encourage people, attendees, to go through the presentation, and if there are any questions, Charles is still here. You can ask them directly in the Q&A, and we can get Charles to answer them at any one time. Thank you.
Yeah, thank you very much, and thanks for having me.